There it goes. Welcome back, everyone. We're going to continue our part 2 now with learning and control and the tutorial.
Yeah, okay, welcome back. Thank you for coming back in after the coffee break. So my name is Lucas, and I'm going to continue with our second part and also the second part of our session, which is learning for control. So yeah, to kick it off, I have to show a block diagram. So we have our controller and our system. And so the standard loop really is we have some kind of reference given, and then the controller provides a control input to the system. And this provides a state back to the controller that we can use in the next loop. But so what this also is a loop that generates data. And so if we apply actions to the system, we get more and more data that we can use to also understand our system better. And so what we do here is we want to use this data to learn about the system, which in the end allows us to reduce the uncertainty that we have about the system. And so the more informative data that we have about the system, the better our model is, and we can reduce the uncertainty, for example, when we're predicting forward into the future. So the first question I want to investigate is how can we act safely under uncertainties? And so I want to start with an MPC example where we have a perfect model. And so the dashed line here is the reference that we're trying to track. And then in gray, we have this obstacle that we want to avoid. If we know the model perfectly, which is just a unicycle model plus some slip model, if we know this perfectly, we can account for this slip, and we can just drive by the obstacle and track perfectly. So what happens if we don't know the slip? Then if we just use the nominal model in our controller, then we actually get to a collision. So how can we avoid this? This is clearly unsafe. So this brings me to the part on modeling uncertainties. So here we have this ground truth slip model that is unknown to this nominal, or nominal MPC. And so one way to account for this is by using a robust version to account for it. So we just take a worst case slip that we assume applies at every state. And so if we do this in a robust MPC fashion now, so we have our nominal model plus this uncertainty bound that we have, we can account for this in our controller. And so now over the horizon, we can plan a trajectory and make it more or less conservative depending on how we chose this bound. And if we choose this bound conservatively enough, we're able to avoid crashing into the obstacle. But what you can also see is that this is conservative. So there's a gap between where we could have gone and where the robot actually went. And so one way that we can deal with this uncertainty is also that we can sample data to learn more about this uncertainty. So again, we have this ground truth model. And if we initially assume we know very little about the system, we can use a Gaussian process. So a Gaussian process is a distribution over functions. And so here, you can see the shaded area is the uncertainty that we have initially about this function. And in blue, you see some functions. These are actually samples from this Gaussian process. And you can see that these samples initially don't have nothing to do with the actual ground truth function. So now what we can do with the Gaussian process is we can collect additional samples, and this will not just update the mean of the function values that we get, but it will also update the uncertainty about the ground truth that we have. So if we collect more and more data from the system, we can shrink this uncertainty and update also the mean of the function. And you can see that the samples that we have from this Gaussian process fit the ground truth much better than the initial prior that we had. So now we already have like a pretty good model. And now we can, again, apply this to our robot example. Oh, sorry, I'm getting ahead of myself. First, we need to take this uncertainty that we have about the model and also propagate it along our prediction horizon that we have in order to account for this uncertainty in a robust fashion. And so there's like various different methods that we can use. One method is linearization, there is sigma points, there's set-based reachability, and then also sampling-based methods. Like all of these methods have like advantages and disadvantages. So one thing that I will focus on are the sigma points. So if you know about like unscented Kalman filtering, this is exactly the same approach. Like the idea really for all of these methods is like how can we take our uncertainty that we have, like typically from like a Gaussian distribution, and push it through a nonlinearity. And like afterwards, it's no longer Gaussian. And so these are all the ways that you can handle such nonlinearities. And yeah, so I use this example because this is like what we did in the lab, and I have like a nice example on that. And so the way that the sigma points work is in the following way. So so we take our robot. So now we assume that the pose of the robot is Gaussian distributed, and also that we have Gaussian knowledge of the slip. And so what we do, we sample these sigma points. These are specific points that we can sample, and then we take each of these points and like we roll out the dynamics from this exact sample. And so if you do this over a time step delta t, you get to like new points in the state space. And then we can fit a new distribution, a new Gaussian, around these points. And so we can do this over and over again to propagate the uncertainty further into the future. And so now we can come back to our initial example. So now that we have this uncertainty, that also gives us like a way to understand like how uncertain we are about the prediction horizon. We can now use this model in our controller to roll out our dynamics and predict with this uncertainty from data. And so you can see that this is much less conservative than what we had before. And so actually we can track the reference very nicely. So we stay clear from the obstacle. And so before I start this video, so this is a real-world example, also on a mobile robot driving in like rough terrain. And so on the left side, you will see the initial policy where you have not collected a lot of data, and you will see that it's much slower and doesn't go as fast. And also, you will see like here the uncertainty tube is also displayed. And like it will be much wider than what you will get on the picture on the right side, where you have the robot after like 3 iterations, where you've like collected a lot of data, and the tube will be longer and also much thinner. So on the left side is the initial one with little data, and then on the right side you have the one with more data, and you can see it's moving much faster, and also like the prediction horizon is much further along the trajectory. And that was the finish line. So came in first, and the other one is still going around, but should also finish in a bit. Okay, so this was how we can account for uncertainty in our controllers. But also, given this uncertainty, can we use it to make decisions around like where should we collect more data? Where should we sample additional data points? And so one framework that does this, especially in the connection with like Gaussian processes, is Bayesian optimization. So a very standard way to sample additional points is like first we have at the top we have just our objective function that we want to maximize in this case. And so you can see the ground truth function in gray and the uncertainty around this function in light blue shaded. And so this is the upper confidence bound method. So where we're trying to basically maximize the mean of the function plus the uncertainty. And so this is a very greedy algorithm. So it's always like trying to maximize the next sample. So if we just let this animation play, you will see, okay, like it finds the next sample and continues to greedily find the best place to sample the next data point. So this gets us to the optimum. However, the question is, can we do this also in a safe way? So maybe it's finding an optimum that's not really safe. And so, research from this lab, what we've done is safe exploration. So where we additionally to this idea of maximizing the function f, we also want to achieve a certain constraint g greater than 0. So now, in addition to the objective, we also have the safety margin that we don't want to get below 0. So while we have the objective that we want to maximize, we also want to make sure that a probabilistic model of the safety margin never goes below 0. And so if we again have our initial observations, we can now say, okay, we want to make sure on the one hand that the mean plus the uncertainty is maximized for the above plot, and also that the mean minus the uncertainty does not go below 0. And so then what we get is we get this set of one, like the safe set, where we are positive, and then also we can categorize the state space into states or samples that would expand the safe set, and also into states that would potentially maximize our values. And so we applied this on a real-world robot. This is for controller tuning. So you have like an initial controller that is not doing very well. But now when you have like this, now you have like this function where you map from the controller gains to the performance using this Gaussian process. And the safety constraint basically is to like not do worse than before. You can sample new points using this safe optimization framework with constraints. And you can improve the performance of the system without getting worse. And so you can see that the performance is getting better. The set point tracking improves. And I think we're almost there. So now we have found the optimal gains, and you can see the comparison from where we started and how we ended. Okay, so what I talked before now was about like learning about myself and doing this in a safe way. But what about predicting the environment? There's also uncertainty about that. And especially predicting other agents. So typically we're not moving alone in the world. Typically there are other agents around us, for example, people. And one choice that we typically have is like, okay, like how will these other agents move? And typically like they wouldn't not just move straight at you, like they would probably evade you to the left or to the right. So you have these two possible scenarios, passing you on the left or passing you on the right. But if you just fit like a single Gaussian to this, you will have a mean that goes like straight at you. And so a Gaussian really is not a good way to model this. And so there's a lot of data that is available from other researchers which you can use to train, again, generative models to predict or to like sample different distributions where other agents may go, depending on where other agents are moving. And so in this next work that I'm presenting, we are using diffusion to model where other agents are moving. So again, you start with like random trajectories, and then you diffuse over time, and yeah, you have like these different modes that you can represent. And then we can account for this in our optimization problem. So this is, again, a model predictive safety filter in some sense. So where you have, at the upper level, like the plan for the robot, and on the lower level, you have a safety filter for these predictions to achieve a non-colliding trajectories. And what's important is that this is interactive. So whatever the robot is doing can influence the other agents in the scene. And this way, we can avoid crashing into other obstacles. And yeah, so we also have this in the real world. So here you can see the mobile robot, and you can see some pedestrians in the lab. And here in the middle, you can see a little diagram where you can see the different paths that have been predicted. And you can also see that this is also slowed down by a factor of 4. And yeah, there's no collisions here when navigating in this crowded environment. And we also took this out of the lab, or my colleague did, and then you can see here on the left is the map where we have like all the observations from the LiDAR and camera fused, and you can see the different predictions of the diffusion model. Okay, yeah, so to recap, I was trying to highlight 3 different questions that we can ask about uncertainty in robotics. The first one really is, how can I learn more about myself, or like what do I know about myself? And I guess the answers there were, we use uncertainty modeling and propagating this uncertainty. The second part is, can we improve without losing safety guarantees? And what we looked at there was safe optimization, or Bayesian optimization specifically. And then finally, how will others react or work in the world? And so what we looked at there was the SIGNAV diffusion that I showed. Yeah, that's it from me.
Let's swap it. We'll kind of do what we did last time, I think, and go through the couple presentations and then have.
Thanks, guys. Good job. Thank you.
Yeah. Let's see if that comes up again. It worked last time.
Make sure both connections.
Exactly.
Make sure both connections on the adapter and the cable itself are fully there, and then try plugging in again.
The adapter, and I didn't follow that. I apologize.
No, it's okay. Are you using HDMI?
Just make sure the connections are tight as switches.
And then give it a few seconds once you've connected the cable.
Okay.
It looks like it's projecting, right? Did it detect it?
That's what I'm trying to. It detects it.
Yeah.
On my.
Is it? Do you need to? Did we switch the input? No.
Is it another?
No.
If it was the same cable the last presenter used, then no.
Yeah.
What's the cable there? Top 2.
Oh, there we go. Sorry about that. Apologies. Hi, I'm Ryan. I have the honor of introducing the third part of this tutorial where we're shifting over towards perception. So we talked about learning to control and control the learning, and now taking a step back and looking at perception and how perception gets incorporated into these things. So if you weren't here before, I'm still Ryan. I'm a professor at Tufts. I run Safe Performant Autonomous Robotics and Control Lab there. And these are the folks that helped contribute to this work. So lots of great people here. And again, you've seen this already if you've been here for the other talks, so I'm not going to get into too many details here, but we'll use a CBF framework for safety involving set invariance and this time decay constraint on our safety value H. So the big question that I want to dig into is, how should perception and control interface? I think a lot of times when we deploy our systems, they kind of have these blocks in them. We need perception to interact with the real world, to understand what's going on in the real world. That feeds into our controller, and then that feeds into our actuators. And what I want to dig into here is what should these arrows be? What should these things be passing back and forth to each other? I think as folks who do learning and control, we probably don't want pixel to torque perception go straight to the actuator from your camera, but it's unclear exactly where those lines should be drawn. And I'm going to start out with my first approach to this. This is actually the first paper I wrote in my PhD, led by Sarah Dean, who I think might be here. But we kind of did the opposite. Instead of doing pixel like image straight to torque as a perception problem, we were looking at image to torque as a controls problem. And we're trying to look at the uncertainty generated by the measurement model, by the perception model, and trying to be robust to that uncertainty. So we have this way of understanding the problem of x hat, our understanding of our state, is equal to the perception module p theta with the measurement model m, which is producing our image, and then that's going to result in, that is equal to the state and some error term e of x. So we've got our state of the system, in this case it's our Segway, our measurement, which is this onboard camera, and then we're going to try to use kind of a robust controls perspective to get a guarantee of safety for this perception-based system. We are assuming a bounded error on our state, which, not necessarily the right assumption for this system, but it's something that we can work with to get a guarantee. And we're assuming a Lipschitz bound on the perception module, which also these Lipschitz constants can be really big, but it gives us a direction forward and also some intuition behind how these bounds and guarantees are going to work. So what we ended up coming up with was a statement that says we can get safety for this system by looking at the uncertainty region where our belief state could be. So our state estimate x hat is this black dot here, and then our true state is within some epsilon ball of that. And we're going to add this tightening term, this negative phi, to our constraint in order to make sure that regardless of where our true state is within this ball, we're going to choose a single input that keeps the whole ball safe. So we have this theoretical statement for this kind of pixel to torque from a controls perspective. And this works on hardware. We deploy the Segway where we're just trying to prevent it from hitting the blocks. It's using this onboard camera, which you can see on the top left for its state estimation, and it's keeping this whole blue tube safe. So the true state is the black line, the estimated state is the dotted line, and we're choosing a single input for the system to keep the whole blue tube safe, acknowledging that the estimated state might deviate from the true state. Now, this worked. And using these concepts of worst-case bounds and Lipschitz constants, I think, gives us a good understanding of, okay, our bounds should be smaller, and we should try to have smoother networks, and this will help us towards generalizability. But it's still highly conservative, and this isn't really scalable to modern AI. And so this kind of put us back on the drawing board and made us question, okay, what should these interfaces be? We can't just apply control to the whole framework, but we really want to leverage each subblock for what it's good at. And this is what we have come up with as to be really effective for this pipeline. Is on the left hand, we have our perception. This is providing us with depth, understanding, semantic data, things we can build maps off of. You've got the LiDAR scan on the top, and then below is our go-to quadruped with the LiDAR unit and its onboard computer we're building this map with. That semantic labeled occupancy map is passed to this central control block, and this is where we're going to build a safety definition off of the occupancy map. So instead of just being we are unsafe or safe based on occupied space, we're saying actually there's a value to being in this region versus another. I'd rather be over there further from the wall, and we're quantifying that with this safety definition H, and then we're building safety filters off of that in this middle block. But we're not doing that with the full torque input or anything. We're giving velocity commands down to a locomotion controller that is then tracking these velocity commands. This kind of sections off the middle bit, this interface between actuation and perception of this internal control block, where we are working with velocity inputs in occupancy space, but we're using all of the control tools that we have to talk about safety as a value, to apply filters, to do some receding horizon control, and things like that in the middle. So we found this paradigm to be really useful, and I'll dig into kind of what we're doing in each of these sub-blocks here. So on the top left, our perception block has just become this little statement that gives us this occupancy map, labeled blue and yellow for some semantic information. And then that is feeding into our middle block that is part of our control. And here we're synthesizing that safety function. So we're going from just a region that is unoccupied or occupied to a value associated with safety in that space. And we're solving this using a Poisson safety function. This is something that the lab at Caltech came up with to get these smooth, safe definitions over the set. Solving Poisson's equation with that forcing function f here, and then enforcing that the boundary, this partial of omega for the occupancy space, is 0. So we're getting this control barrier function style function generated off of the occupancy map. Once we have this definition of safety, we'll move from the center block to the right-hand side, and we have our safety filters. We have a model predictive controller with a CBF safety filter in it. This is helping us improve performance. So the model predictive controller is giving us performance alongside safety, but it is taking some time to run, and so we are also then passing that through a CBF QP that we can run really quickly. That is then getting passed to our hardware with a associated tracking controller, which is doing the low-level locomotion. And sure.
So I'm looking at your figure. So that surface which is above the plane,
yeah.
look to me corresponds to those squares. Is it just an illustration?
This one I think might be rotated, but yeah, it's just an illustration. Yeah, sorry about that. Yeah, apologies. Yeah, I think you're right. I think it should be rotated by like 180 degrees or something. But you can see the actual demo on the bottom. So these are associated. There's the left-hand side is the perception. So we have a camera above the environment looking down. It's segmenting the ball. So there's this ball rolling through the space and then generating the occupancy grid in the middle. And so you can see as the robot rotates, it buffers the ball in different directions. And then on the right-hand side, you can see the safety quantification that we're building up, this H value. And then this feeds back and we get the closed loop behavior that you're seeing in the perception there. So just another demo that's a little easier to see. Same thing going on here. So we have an overhead camera. It's generating the safety descriptions, these H values on the left-hand side on the television. And the quadruped is using that alongside a model predictive control CBF filter to avoid getting hit by the balls. Then we've done this in a bunch of different scenarios. So this is on a humanoid robot. We now extend it from just position to also orientation. And it has this big beam that it's trying to carry, and that's changing how we buffer the occupancy region. You can see that in the Poisson view, this red square on the bottom. And we're commanding it to go back and forth, and it wants to be rotated like 90 degrees so it can't pass through like it is now. And we say, oh, well, actually, we want you to move through the space, so the robot realizes, oh, I have to rotate in order to pass through safely. And so we have this single value of safety, this H, with respect to our position and our orientation that we're planning through, and that allows us to navigate this space safely. We're using this overhead perception in order to generate the occupancy map, building safety on top of that, and then using it to filter velocities, which are sent to the locomotion controller to track. We can also, because we have a single value of safety, we can do this for really complex systems. So here's our robot manipulator, and we're defining safety for the whole body. So we sample a bunch of points on it and are able to calculate this single H value for the whole system. So there M is moving the ball around. You see we've now subsampled into each link to represent what safety is for each sublink of our Franca arm. And then M is blindfolded, so we're not pre-programmed trajectories. She's moving this around, and it's avoiding the obstacles. Same thing here. We are commanding we're commanding motion for the silver arm, and it's causing the white arm to move around it. This was the video that Zach showed earlier. Now we're kind of seeing it from the other perspective, not the CLFRL, but the obstacle avoidance here. The humanoid is running. It is simultaneously using its perception to build a map around it. That occupancy map is being converted into the safety value that we're then using the MPC plus CBF filter and a CBF QP to generate control actions for and move through. So it's avoiding on the left-hand side this block and then the person on the right, and that's modulating its trajectory as it runs forward. So we're excited about this idea, and we have this now single safety function that represents safety for our whole system, and we're looking at applying it to bigger things. So potentially for navigation problems, this is like a cityscape almost of like lots of things going on here. We can represent safety for the entire environment with a single function. And so kind of the key insights, this has been really useful, but we were missing one of the important components from perception. So I talked about it helps us generate maps and occupancy grids, which we found very useful, but it also gives us semantic information that we haven't used up to this point. And so the key insight that we're going to use to include the semantic information in our safety filter is that the safety comes from the alignment of the dynamics with the gradient of h. So what we really care about is that the dynamics point inward on the boundary of our safe set. But they don't exactly have to match the gradient. It's really about this direction. And so we can use that to modulate what safety means and how we're enforcing it on the interior of our safe set. So we can change the boundary flux and the magnitude of the gradients along the interior of our set. So on this we can change the magnitude at the boundary and adjust where our filter gets enforced. And so what we do here on the right-hand side is we're adjusting, instead of having this nabla h term that we're using to define our safety filter, we're going to switch it out for just this v. And we're going to enforce in the center block that this v, this Laplace guidance function is what we call it, has to be aligned with the gradient at our boundary. But we can adjust its magnitude. And this allows us to scale where our safety filter gets activated. And so what that ends up looking like is larger fluxes. So if we change that magnitude on the boundary, the larger flux causes the filter to activate further from obstacles. So there's this black arrow on the right column for the variable flux, where we're looking at this red line is where our filter starts to get activated. On the left-hand side, if we have a constant flux, kind of what the standard control barrier function would do, they have these activation lines all about a similar distance from the obstacle. For the variable flux, these now have different distances. So for a large flux, it activates further from the obstacle. We consider this potentially a risky labeled obstacle. We're going to want to start enforcing our safety filter a little further away. For smaller fluxes, we can get closer to the obstacles. We say they're less risky. They've been semantically labeled as something that is okay for us to approach. And you can see this in the closed loop trajectories at the bottom. So on the left-hand side, everything is given a wide berth, but on the right-hand side, we've now decided there are certain obstacles we can get closer to and slide along, and that's okay. And we can use this semantic information directly from things like YOLO. YOLO is a semantic, we can use it for semantic segmentation. And we have this picture of chairs and a person. We generate this guidance field and say, the people need to have larger boundary flux. So we want our safety filter to activate further away from the human than the chairs. And you can see that in these activation zones on the right-hand side. So the safety filter is going to activate earlier with respect to the people than with respect to the chairs. This is a way of embedding this semantic information. The other tuning parameter that we have that we realized is that we can use the interior guidance field. So not only can we modulate this on the boundary, and when we modulate it on the boundary, it has to be aligned with the boundary gradients, but on the interior, it can kind of be whatever we want it to be. And so we have this additional tuning knob to adjust the behavior based on the semantics of the environment. So what we did was we embedded this internal layer and said at a distance r from our obstacle, we now are just going to define what our Laplace guidance field is, and this is how we're enforcing our constraint. So we're adding this third line to that center block. So we, on the boundary, have to align with our CBF gradients, point inwards, and then interior, and r distance away from the obstacle, we just get to set the direction that we define as safe. And what this allows us to do is, with the boundary flux, we say humans are riskier, so we want to avoid them, give them a little bit more berth. And then with the interior guidance field, we can say people like being passed on the right. So we influence the control velocities that are being sent down to the locomotion controller and say, I want to rotate around the person on the right-hand side. And you can see in these trajectories, going around the human, which is this red dot, it prefers to go clockwise, and then going around the regular obstacle, which are just these blocks, it can go either way. And so when we deploy this in closed loop, we segment the people, we semantically label them as humans, generate this guidance field that says humans are riskier than other objects, and I want to pass them on the right if I can. And we get this closed loop behavior on deployment. And we've looked at deploying this in a bunch of other spaces too. So on the top left, this is our hallway example. Then on the bottom is the same example you saw before, just from a different perspective. We put this in the cafe over at Tufts, and so the quadruped is walking back and forth in this busy cafe, avoiding collisions and passing people on the right. And then we also deployed this on our humanoid, so directly transferred. What's nice about this is we're interacting with the perception via occupancy maps and with the robot via velocity commands, and so it transfers directly the whole pipeline. So just as a few concluding thoughts here, the kind of key takeaways were this, I think, is a very useful paradigm for perception to controlled actuation of like, what should these interfaces be? This isn't necessarily the only answer, but it's an answer that we found to be very useful. The center control block here can take in semantically labeled occupancy maps and then output safe velocity commands that embed this understanding of safety and semantics. So we can use control as this kind of interface between perception and reduced order dynamics at the other end. And this adjustment to the safety filter via these Poisson safety functions and the Laplace guidance fields gives us additional tuning parameters for the MPC CBF controller and the CBF QP to adjust the behavior to fit the semantics of the scene. Thanks.
We'll switch up, and then after this, we'll have time for discussions and questions on
Perfect.
the second section.
Oh, I almost forgot. Sorry, I have a couple of cool videos that, if I have a minute. So we've got our quadruped with a dog, a golden retriever, interacting, running this same collision avoidance with the Poisson safety filters. And it's a herding dog, so it's exhibiting herding behavior. It's awesome.
I'll sort of add to this video actually, because I think this is sort of a cool like transition point that happened. Our safety filters used to be such that dogs would bark at it and get annoyed by the robot, and then when we got this good enough, we passed this performance boundary where the dog started interacting like an animal, and again, it herded it like 5 times in a row, I was told, right? So it just kept herding it, which tells you you're starting to get into this uncanny valley of robots acting like animals, right?
When we switched off the safety filter and were commanding it by hand, the dog did not like it. But when we ran the safety filter, for some reason, the dog really was okay with it, and it was great. And then just as a final thing to end, because of the World Cup, we had to end with football. So, all right, thanks, everybody.
Great, thanks, Ryan. Okay, great, you're up.
All right, my name is Siki. I will, finish up the last part of the tutorial session core content. So I'll continue with Ryan's discussion on perception-based method and then show some ideas why semantics is important for safety. So as robots move in unstructured environments, they need to operate based on perceived inputs. And this requires tight coupling of a couple of functional blocks, like localization, mapping, and control. So localization is trying to estimate where the robot is relative to a map. Mapping is trying to distill from the perceptive input a representation of the environment, and then control will take care of this translation from the environment understanding into action. So if we look at the ways to represent the environment, just for geometry, there are different ways of capturing where the objects are. Typical ones include point clouds or occupancy maps, or there are also implicit methods such as superquadrics, truncated sign distance functions, or explicit methods such as meshes. All of those are just different ways to represent where the physical boundaries are. So over the past years, we have seen a gradual shift from trying to obtain geometrically precise environment representation to semantically rich representations. There are many motivations for why we want semantics in the environment map. On one hand, this would enhance reliability in mapping. For example, if we observe the same area over different frames, we can better associate objects with the semantic information. And on the other hand, semantic information can also help to differentiate dynamic, semi-dynamic, or stationary objects, and this would inform which part should be part of this the build map, and which part should be updated from time to time, and which part should be masked out in the mapping process. And lastly, with semantic information, this would also inform downstream robotic tasks, for example, object navigation and manipulation, or understanding safety constraints. So this trend of embedding semantics is partially driven by the availability of large-scale data sets, as well as continuously improved algorithms to distill trends from those data sets. And those efforts were started from ImageNet, which was one of the largest data sets from 2009 for image recognition tasks. And then 2012, so AlexNet was the one work that shows promise of using networks to learn capable models to actually recognize images. And then there's continuous improvements. For example, ResNet was the time where we showed that this can actually surpass human performance. And then from 2017, this was the first transformer model, and going onward, seeing a growing trend of exploiting scaling law, which is a belief that if we have more model parameters, larger models, and more compute, we can build more capable models. So one of the commonly used foundation model or vision language model is CLIP. Just as an example, so with this model, this would help us to build open vocabulary capabilities. And this is achieved through contrastive learning. So intuitively contrastive learning enforces the learning algorithm to learn a shared embedding space between multimodal inputs. So here we have text and image, and if they correspond to similarly contextual similar concepts, they're encouraged to have high similarity scores. And conversely, if they're dissimilar, they're discouraged to have high similarity scores. And this is one example of how this model enables one-shot inference. So instead of using typical softmax over a closed set of objects to know what is shown in the image, this model CLIP, we can query, for example, this is a photo of X, and X is some word we can define. And then by computing the embedding of this language input as compared to the image, we can determine what semantic category best match the input image that is shown. So for 3D representation, this has been used a lot to enrich the semantic understanding of the spatial space. So with this CLIP-like model, for example, if we build an environment map and each pixel has its CLIP features, then we can query the map and say, find a place to sit. And with this contextual or open vocabulary capabilities, this model will tell us those are the pixels corresponding to a couch, which which is appropriate for sitting down. So given this geometry and semantics, the question is how we can best leverage such information for robot decision making. And for the rest of the talk, I'll try to show how we can use semantic information and also the geometric information in typical robotics pipelines, going from reliable mapping in changing environments to fulfilling language-instructed tasks, and then to deriving geometric and semantic safety constraints. So just to motivate why semantics is useful, this is one example where we see that a lot of the real-world environment will undergo semi-static changes, meaning, for example, furniture can get moved or appliances can be shifted over time without the robots continuously observing such changes. And if we don't systematically account for such changes, the map may have artifacts or phantom objects, and this would, in turn, negatively affect both the localization performance and control performance. So how do we resolve this problem? what we can do is we can explicitly model the geometric change and the stationarity score of individual objects instances in the environment, and then derive a Bayesian update rule to update those object states as we gather additional information. And here the measurements consist of the measured geometric error and the prior stationarity score or prior stationarity label that is derived from the semantic class of the object. So if this is a box, it is likely to move, and then this score S would be 1, and well, if it's a shelf that is less likely to move, it will be 0. So to keep a consistent map, we can leverage the stationarity score that is recursively estimated over time to determine whether a certain object has been moved or not. And if it has been moved, then we'll remove that part of the object from the map and then rebuild this based on new observation. So here's a video showing how this works. So if we have a ball here, the right top corner shows the stationarity score estimates. So once the object is stationary, this will convert to 1. And if we remove it, this will drop below the threshold. And if you see the map down there, the point cloud gets removed. And if we introduce another ball, this again is introduced to the map with the corresponding stationarity score being tracked over time. And if we put the other ball back, we can re-identify that this is the same instance, and then again, we can keep track of the stationarity and update the map correspondingly. So with this explicit stationarity score modeling, we can keep a spatially and consistent map of the environment that will facilitate downstream planning and action. So this is one example. If we have such a map, we can perform object navigation tasks. Here, if we ask the robot where's the glasses, then they can use cliff features to query contextually relevant areas, such as closer to books, and to find those objects more efficiently. So how do we leverage the map for safe control? This was also briefly covered, I guess, in the other techniques. So if we have, for example, a representation of the environment like an occupancy slice, we can convert this to something like a sign distance function or Euclidean sign distance function, which really maps each point in the space to a scalar value that captures the distance to the closest surface. So if we're at the surface, this value will be 0. If it's in free space, this will be positive. And then if this is in either occupied or unobserved space, this will be negative. So we can use this truncated Euclidean sign distance function as a contributor function to enforce collision avoidance constraints. And this is one example where we have a mobile manipulator performing sequential manipulation tasks while the environment is changing. So the semi-static mapping takes care of reliable representation of the environment, while a perceptive MPC framework is used to enforce this collision avoidance constraints. So kind of showed how we can use perception inputs, both the geometry understanding for collision avoidance and the semantic information for performing tasks. So another question is, what about safety for everyday scenarios? So beyond collision avoidance in real life, the robots should be able to comply with constraints that are not just geometrically defined. So for example, if we have a robot operating in the kitchen, I should know that metallic materials should not be placed in the microwave, or pressure cans should not be placed on top of a stove, or keeping heavy objects away from fragile items. So with the models I briefly introduced earlier, the robots are increasingly capable of understanding the semantics, knowing where they are, and understanding how they relate to each other, and knowing which part of the environment is relevant for the task at hand. So the next step is really trying to bridge the semantic understanding and translate this into safe action. And there are many ways of doing this. So one of the possible ways to leverage both this semantic geometric representation of the environment together with the reasoning capabilities of language model to derive semantic constraints beyond collision avoidance. So with this example pipeline, the robot is taking in RGBD images as the input. And with this RGBD images, we can build an object-level semantic map of the environment. And with this map, we know what objects are in the environment and how they relate to each other. And then we can use this information to build a set of queries and ask a language model whether it is safe for certain relationships to happen. So for example, whether it is safe to move a cup of water over a laptop, or whether it is safe to put a strong bunch closer to the laptop. And the language model can give binary, or will make a binary decision, yes or no. So it is not safe to move liquid too close to electronic devices, while it is safe to move the sponge close to laptop. So with these binary decisions, we can distill a set of semantic constraints that the robot should be compliant to or with, and then together with the environment map, we can translate this into analytical forms such as control barrier functions to enforce such constraints. And this is what we call semantic safety filter. And this operates in a similar manner. So if there is a teleoperator or a learned policy, this can compute any inputs, and this will be passed through the safety filter, and the safety filter will be responsible for enforcing the constraints that were distilled from the semantic inputs and the language-based reasoning. And after certifying the inputs, it's then sent to the robot system. So here are some examples that we have shown in the kitchen. So with the semantic safety filter, this robot will be prevented from putting too heavy objects closer to fragile items. We're preventing the robot from putting the pressure can over the stove. And preventing plugging the fork into the power plug. So just to conclude, so what we have seen is robots are increasingly capable of acquiring semantically rich representations of the 3D environment. And reliable leveraging the semantic information for safe robot decision making requires tightly coupling perception, reasoning, and action in closed loop. And there are still many open questions in this area. For example, how do we categorize semantic safety? Safety is in general a very broad concept. And what modalities are necessary to enforce what kind of safety constraints that we care about for certain applications. And also on the environment representation side, what is the best representation to facilitate downstream tasks? Do we need, for example, beyond geometric understanding kinematics, like should we model articulation or other dynamics properties of the environment for such reasoning capabilities? And then lastly, how to account for both geometric and semantic uncertainties in closed loop and possibly actively minimize them? And how do we reliably estimate realistic uncertainty bounds that are not too conservative for real-world deployment? So answering some of those questions really requires solving the problem at the intersection of perception, reasoning, and control. So with that, I guess I will conclude my part and pass this to Angela, who will be presenting the conclusion part online.
Give us 1 second. All right, Angela, you're on.
There she is. Perfect. Awesome.
Okay, welcome everybody. So I have the pleasure to summarize this. I also like to thank really my current and former members of my team who are there in person, and please talk to them. So Mahati, Lucas, and Siki, thank you so much. I'll go back to our initial summary, right, or initial block diagram. So he really wanted to show control as guidance for learning. This is kind of the number one, right? We show that we can achieve data efficiency, safety, and better performance or explainability by leveraging control insights when designing our learning algorithms. Then in the second part, we showed how learning is used for control. And here learning can give us performance, and the control insights still give us the necessary guarantees. And lastly, in part 3, we looked at perception, because perception gives us understanding of the world, but control can still give us the necessary guarantees in terms of the robot actions or any system actions in the real world. So you saw a lot of methods. I try to summarize them. I think what is really exciting about this tutorial is that very similar methods have been used in Aaron Ames' lab, in our lab, on different robot platforms, mostly humanoids and mobile platforms. And so I hope this also shows you the generalizability of these methods to different applications, maybe even beyond robotics. Right? And so what we showed in part 1 was techniques like CLF and CBF guided RL and predictive safety filters, which guided our learning and it enabled efficient learning. Then we saw safety filters that enable safe learning and deployment of possibly complex, generative AI models. For example, methods such as constraint diffusion policies or LLM-generated plans that were safety filtered through a predictive safety filter. And lastly, control-driven regularization in learning was used to achieve stable closed-loop behavior in the real control loop, for example, through Lipschitz neural networks. So these were the type of techniques we have seen, and they worked on various robotics platforms, but I could see this also happen in very different application areas, actually. And then we take the other part, like using learning for control. And a core theme was probabilistic learning models that helped us to kind of define the distributions as we gather more and more data, and therefore to reduce conservatism compared to robust control techniques. These probabilistic bounds also enable safe exploration, and they can be used to predict not only the robot's own behavior or the system's own behavior, but also the environment. And you saw this, for example, with humans in the environment. We can predict their behavior in a probabilistic manner and take this into account in the control. And then in part 3, we really close the loop by looking at perception and how we can model the perception uncertainty and take this into account, how we can operate as a result safely in unstructured environments, because we can perceive the environment and use the right environment representations that are amenable to control techniques. And the final part we have seen both in Ryan's work as well as what Siki presented is what is if we understand the full semantics of the scene, not only the geometry, but we understand what we see. Can we use that to increase the safety of autonomy, especially in human-centric environments? So I hope these methods stick with you, and you also get excited as we are about these different kind of streams that are often treated separately, and we want to give you this broader overview. More or less, it also boils down to something that we analyzed in a survey paper a while ago. Right? Often model-driven techniques, you can look at them as in the top plot. The model describes a small area of the world very well, and in that green area, we can give strong guarantees. So strong guarantees in very specific contexts, but the challenge is generalization to new contexts. Like, the general vanilla learning-based methods, they have high generalizability to new contexts as long as we have some data, but providing hard guarantees is really the challenge. And finally, I think all the things we showed you try to combine the methods such that we have the benefits of generalizability with more data for contexts that we haven't seen before, and still provide certain safety guarantees and are also able to efficiently explore the unknown. And so this figure was taken from one of our survey papers called Safe Learning in Robotics. So if you are interested, you can look at this. There's also quite a bit of open source code related to the survey paper. And we later spun this out and try to make this a real benchmark that you can benchmark model-based techniques and reinforcement learning techniques. And this was not previously possible because things that we care about a lot in controls, such as constraints and prior knowledge, they're usually not embedded in the typical RL benchmarks. And so this benchmark allows you kind of to see the trade-offs between, how much prior knowledge you have versus how much data you need. And still, and also evaluate against, constraint satisfaction goals. And there's also a webpage, saferobotlearning.org, where we summarize some of these materials and also recordings of previous workshops. And if you're really new to this, I want to just briefly mention, I'm teaching a course or a sequence of courses actually at the Technical University in Munich. And we now are in the process of publishing our lecture notes and the corresponding Jupyter notebooks. And so here we really go from the foundations of optimal control and dynamic programming towards model predictive control, model learning, and connect this to reinforcement learning and deep reinforcement learning, which basically is all the same, all relies on the same theory. And so if you're really new to this, this may be interesting, so you can scan the QR code. And finally, maybe one thought in general, I think you are all more a controls community, and model-based control and reinforcement learning really solve the same policy synthesis problem. We want to find the control laws, right? So it's about controller synthesis or policy synthesis if we talk in the reinforcement learning language. And model-based control gives structure and basically acts as a hypothesis filter. So while reinforcement learning is more a hypothesis generator, like generating lots of data that helps us continuously to test and hypothesize about good policies. And so because these are really very much connected, we started also looking at properties of them in a more sophisticated manner. And so I just wanted to highlight this a little bit to show you they are related and they're different kind of properties. And, they relate, for example, to how good is the performance, right? And better performance is further outside of the circle. For example, how much model knowledge do they require? How much data do they require? How robust are they to changes? How well do they generalize? And so we have just started this. So this is just a teaser. It's also not published yet. But you see, for example, if I have a perfect nonlinear model, we are very good in one area, performance, also generalization, based on how we define generalization, and we don't need any data. So we basically assume we know everything, right? And then if you go into model-free RL, we get kind of the advantages in a different area of the circle. So this is kind of things we are also more broadly exploring, because it ultimately all comes down to we want to find control policies. So where does all of this go next? Sometimes I look at it in this form. So we had the stage of automation where we used mostly prior knowledge, such as Newton's law and physics, to describe the world and then get really reliable policies. Then there was this phase of using robot-specific data, and you saw quite a lot of examples today where we use robot-specific data to deal with the complexities of the real world. And I guess we now see a big shift where we have internet scale knowledge, such as language and image understanding, at our fingertips. And I think this is also an opportunity and a challenge for robotics and for control specifically. And so if we zoom into this kind of how do we bridge kind of from robotics specific data, which we have shown you, to more this large scale understanding of the world and large scale data. One way to bridge this for robotics is that we also leverage synthetic data in the process, because we don't have cheap language data and image data is not enough, right? And so we recently did something to just show you that there can be almost a paradigm shift in controls to a certain extent. We basically built a simulator called Crazy Flow, and there to show the potential of GPU accelerated parallel simulation. We throw a drone in the air, and while it is flying in the air without a control policy at all, a reinforcement learning algorithm runs on a GPU accelerated simulator, and we can find a policy to stabilize the drone, while it is being in the air. So basically within 500 milliseconds, right, through massive parallel simulations and a very good sim-to-real transfer. And we can, do things such as, for example, here we have a planner that doesn't explicitly take into account all these constraints, which would be difficult, but instead we just do brute force sampling based method, but based on the physics of the robot, we kind of can do 500 rollouts in 20 milliseconds and basically find collision-free trajectories just through massive parallel rollouts, instead of solving the optimization problem basically in a sampling-based manner, instead of like through, let's say, a nonlinear optimization. So yeah, and similar, approaches of using synthetic data was also a big enabler on the computer vision side, for example, to understand complex environments and objects with models such as SEM3D. And then if we can use these parallel simulators plus maybe internet scale knowledge, this is just a hypothesis at this point, such as, for example, YouTube videos, maybe we can give robots a lot of skills. So here, this is a preliminary work where we just look at dog videos and then we train similar policies that are very robust to disturbances in a simulator. And so similarly here we show that various other methods take quite some time or a lot of reward tuning to get good results, while by recording a dog from stair climbing, we can use that as a prior, similar to what Ryan and Aaron showed for humanoids. Like we can learn from 2D videos. So this is a kind of combination of real world data, but 2D videos, which don't include the real physics, plus a good simulation engine in the background that allows them to do RL in simulation and bridge to the real world. But this is not the end. This is really the beginning of this field. So I hope many get excited, or maybe you can also connect your own work to the lines of work we have shown. And there are many more questions to be answered. And so here are just a few, right? They're by far not complete. But what about if we learned a lot about the robot dynamics, and we showed a lot of that in this tutorial, but learning about the environment, we only touched at the very end. And open questions are how to effectively learn and interact with humans in shared spaces. We saw a some early works in this direction with humanoids among humans, how to best represent the 3D environment, right? So I think there's a lot of controls knowledge we need to translate the perception models into something we can use to compute actions from, and what information is also necessary such that robots can safely interact in complex environments. Another question is how do we reason about safety in context-rich scenarios? And what you haven't seen in this talk, at least, is manipulation, right? So context-rich scenarios would, for example, include that as well. And how can we best leverage large-scale synthetic data in the closed loop? And this is some of the ideas I showed you. Maybe there's a paradigm shift that we really go towards large-scale parallelized simulations to solve complex optimization problems in real time. So, yeah, to conclude, we structured it in this following way because we really saw that control influences learning, learning influences control, and control really needs perception to work, at least in robotics. And often what we see in papers is basically these verticals, right? So for example, people talking about reinforcement learning in simulation and briefly show that it may translate to the real world, but don't show you much about how. So often this is done in these silos, especially a lot of work just looking at perception, but not connecting it into the closed loop or not connecting it to robotics. So I hope this tutorial helped you kind of, see a bit the bigger picture and how these works connect. So thank you so much. Thank you also to all the previous presenters. And happy to answer questions, but I think all the previous speaker of the second session should come on stage and answer questions. Thank you.
And so we should bring on, and we have a few minutes for questions for the second phase, but I want to sort of just echo what Angela said, and it's really, and I've looked at her work over the years in many cases. She's been a leader in bringing in these new tools, reinforcement learning, et cetera, into the control sort of paradigm and bringing the control paradigm to reinforcement learning. And I think that's really the lesson of not just reinforcement learning, but all types. And that's kind of the lesson of today. I think control as a community has incredibly powerful tools to bring, but we need to adapt to the landscape of the moment. Things like GPU parallelization, domain randomization, like this massive compute at our fingertips. And if we don't bring our methods over to there, they have a danger of being lost. And then people will roll out this stuff without the formal guarantees that we can provide. So we really, I think it's a moment that we as control people should try to meet in the learning-based methods, and that's what this workshop was all about. So without further ado now, though, I think we can close with some questions, especially for the last speakers and the last segment of this tutorial. So, mic time. Who wants to lead off for the questions? I know once we get someone going, they'll roll out. So who wants to be the first? Go ahead, jump up to the mic if you can, or okay.
Helpers, don't forget to turn on the mics on the mic stand. Press the on button.
How do you deal with this perception uncertainties acting as a stochasticity in the dynamics, especially with your stochastic CBS setting, especially if this state estimation uncertainty is not an additive Gaussian or additive white noise?
Totally. So the first talk versus the second talk are kind of trying to solve the problem from two different dimensions that we're trying to meet in the middle towards. So I don't think we necessarily have a solution yet, but we're trying to come at it from both sides. On the first one, I talked about safety for the collision avoidance in the setting of the common filter, where we're giving safety guarantees with respect to the belief state. But you're totally right. When you have alternative distributions or different understandings of your belief state that aren't just the Gaussian the Gaussian, it can be a lot more complicated. And so I think there's sampling methods that you could possibly use in that direction to get more or generative models, things like that, to capture more complicated belief representations. On the other side, what I presented in this session, we weren't dealing with the uncertainty in the perception model yet. But building that into the occupancy grid is something we can do with the risk type stuff I was talking about, where you can change the magnitude of the boundary flux and say, I want to activate sooner. So there's a direct connection there to the robust control style input to state safety work, where you want to activate sooner because you think this thing is riskier. Now, connecting the probabilities is something we're trying to do. So this is like pushing those two directions into the middle to get both of them at the same time. Does that answer your question?
Yes.
Thank you.
Other questions? Right here in the middle, and back there. So we'll do this one.
Hi, thanks for the talk. So I don't know who to ask the question, so I'm going to ask it to everyone. Basically, I was wondering, like, there seemed to be a theme throughout the talk, which was about, the model is overly conservative in a lot of scenarios. And so I was wondering, have you guys or someone else has explored this possibility where instead of going like fully formal versus fully perceptual, you can start with formal guarantees and have the model propose relaxations instead of coming up with these sort of constraints from scratch, or starting with just formal. So start with formal and then have the model just propose relaxations.
I think the way I think about this a lot is like we start with the model and we know the model is wrong. And so that's where we add the data to get the additional performance benefit. You could bound the wrongness, or you could try to learn the wrongness and compensate for it that way. And now you have a better model because you started with something that was good but wrong, and now you have something that's better because it's data driven. And now you can push the boundaries of that performance because you've now got a more accurate model. Potentially driving in the direction of what you're talking about. I don't know if you all have thoughts on his question.
Yeah, I guess one way we did it was with probability modeling. So we can start with something more careful if we're more uncertain about the model. So we capture how wrong the model is. And then as what Lucas covered, as we gather more data, we can be more performant over time. And another idea is, for example, if it's operating in an environment, we can possibly like servicing something conservative and try to actively explore both on the dynamics end or the environment side to minimize that uncertainty. So starting with something robust with hard guarantees, and then eventually reduce that conservatism by gathering more data from different sources. Yeah.
We had a question back there. I saw that one next. And then we can go here.
Thank you for the wonderful talk. I had a question related to the tasks that the robot are supposed to carry out in real world and the sensing modality. So for instance, we have ultrasonic sensors, we have millimeter wave sensing and radars and whatnot. And so I know that most of the talks are about vision and audio and things like that, but is there a comprehensive understanding of the sensing and the tasks, and what kind of sensing would be good for what kind of tasks, and maybe how does that lead to robustness of policies and the learning performance and things like that? Like, I don't work in this area, so I'm just trying to figure out if there is an understanding of different sensing for different tasks and whether that leads to better performance or not.
Yeah, maybe I can say something. We did this in the context of self-driving, where we looked at LiDAR versus 360-degree radar. So the first thing I have to say is state estimation from multiple sensors is a complementary problem to the control problem. You have very similar questions because often there's still an underlying model, at least a simplified one, such that you can deal with outliers. And then, for example, there we found that in many scenarios, where LiDAR was supposedly not so good, such as rain and dust and snow, or even snowstorms, LiDAR can actually be quite robust if you do the right state estimation with an underlying model. And so I think the interesting part on the perception side is that it's almost it's the complementary problem, right? And they have the same questions, for example, what model to use with what uncertainties.
I think like something that's also relevant for us when we want to use semantics. A lot of the semantic work from like the computer vision people, they always rely on vision because a lot of data is available for that. So I think for other sensing modalities, this is maybe not as much available. So I think if people work on this more and like release data sets and maybe potentially models as well, I think this will also be easier to integrate into these kinds of pipelines as well.
Thank you for the great talks. My question is a little bit more philosophical. So I see a lot of like some nice theories and so on. But the question is, what is the invariant that survives across all three layers? So often what I found was when I start actually have something working for one layer and try to pass this one to the second layer, and the error becomes small. The error is actually small, but when I pass this error to the next layer, it becomes almost impossible to prove something. So where we need to start and end. So for example, do we need to start actually proof from the perception layer or controller layer? All these things is very something we need to address, but I don't see how, right?
So this is a little bit of what I was trying to get at. In what I was talking about of these three blocks of perception, this middle layer control that's operating in occupancy to velocities, and then this low-level actuation, which is including our locomotion. And there, I was showing the direction in one way of passing the occupancy map down, then passing the velocity command down. But really, there's a second direction also. The locomotion controller passes back up some sort of convergence around your commanded velocity, and then your middle layer control passes back a buffer around your occupancy grid or some distribution over where you're actually going to go given that. And so there are these connections and they're passing both ways, and that lets you close off your blocks a little bit and like study them in isolation and then connect them back up when you want to deploy the whole system. Absolutely. So
if I can add to this, I think it's a fantastic question. I mean, the question is really how to understand layer control architectures at a macro level, right? And of course, there's a bunch of work that's been done on this from a formal methods perspective. Assume guaranteed contracts between layers, right? For example, among others. Formal methods, of course, are going to sit at a top level, and what do you do across the layers? But I think as like a control community in particular, this is still like a really new and open area for us to be thinking about, especially from the perspective of robotic systems as inspiration. Not that we need to be concerned with that right now, like in the sense of mathematically, but it should give some good guidance. And I think actually, we've been doing a lot of workshops on this at CDC and ACC, thinking about layered control architectures. I think there's actually space for new formal tools, like category theory actually can play a really big role in these kind of architecture discussions. So I think there's a ton of math to be done on the other end of the spectrum. And I think that's where, as a community, if we can run the gamut from math to learning to actual robot implementations, that's when we'll have a better sense of the entire architecture.
Great. Thank you very much.
Maybe I saw one more question, and then we're probably nearing time. When are we over? Probably now, right? 3 minutes. 3 minutes. Okay, great. I saw a question go on back there. Yeah.
Thank you for the wonderful presentations. So I wanted to ask, what if the safety requires manipulation of the environment? And do you think the safety filter framework allows you to generalize to those kind of scenarios, or would you prefer decoupling as we would typically do in control scenarios, the task planning stage and the motion planning stage? So for example, if the robot has to pass through a puddle because the safety requires it, so is this something that's the current framework that's introduced in this tutorial, could that be extended? So right now, I think we've covered just the avoidance scenarios, but what if we require manipulation or moving some obstacle around? Thank you.
I have I just want to, I mean, it's been studied. So we didn't talk much about manipulation today, but I want to kind of mention a lot of the methods applied here do work. Manipulation is its own challenging problem, to be clear, and has unique aspects, but a lot of things do apply. Like the sampling-based predictive stuff that Angela showed, it works really well in manipulation. We've actually played with that in my lab as well, rolling out trajectories using a model to decide what to do next. From the safety side, you know, there, for example, has been work done with CBFs on the force of contact to create like good contacts with the world and the environment. So I think in the end, these methods are invariant to platform, and they can be applied across stack, because it's not just a platform manipulator versus humanoid, but also what's your notion of safety? Is it force-based safety constraints? Is it, you know, acceleration constraints? We've done CBFs on jet aircraft for which like the G limit becomes a big deal, or all the way up to task-based level collision avoidance. I think at every level there's unique challenges. I don't want to pretend like the same thing just universally applies in terms of you just drop it down. You have to understand what things mean at that layer. But there is a consistency with math across all the layers and the ability to apply these kind of approaches philosophically, including manipulation and locomotion. I don't know. And please.
Yeah, I totally agree. I think philosophically the math lines up great. And I think what has been motivating a lot of the collision avoidance stuff is the math applies particularly easy there. You wind up with this control affine dynamics with a linear constraint, and you can apply it really quickly. You have a QP you can solve as an if statement. But we're at this really fruitful time if we have a lot of compute and we can go towards more complicated dynamics like contact-rich manipulation and start to generalize the thing that in theory should generalize, but we haven't been able to do it on hardware yet. So I think it's a really exciting time to study that exact problem.
And I think just to add to this, there has been very recent work on CBFs for local manipulation. There you just have the hands kind of like your fists to grasp something like a box. Right? I think it's still simplified once you kind of work with, you know, real hands. For fine manipulation, I haven't seen as much, but I also do think these methods apply, right? And often we also don't learn from, or RL people don't learn from failures, and just learn from good data. And so they are quite naive in this